Hi everyone. Today we will be presenting our final project for M20, the MATLAB class. Our project is on heat transfer in beams. So essentially, beams made of different materials have different properties for transferring heat, and we're going to be simulating that by looking at different material properties. So when we're looking at our materials, we have their names. Of course, we have to differentiate between the materials. We have their density, conductivity, specific heat, and diffusivity, which all calculates for the distribution, basically how heat transfers among the materials. We have two beams, and they're going to be of either similar or different temperatures, lengths, and material type, and we are going to be simulating through a 3D graph and or a heat map how that heat transfer works.
First, we'll walk you guys through a run of our simulation so you get a feel of how our simulation looks from the user perspective before showing you how the actual code works so you get an idea of what the computations are that are happening. So first, we'll run our simulation. So the user is first greeted by a brief description of how the simulation works before they get to define all the materials. You can define the width for the beams. I'm just going to be using values that I know have produced clean results, but you can choose whatever values you want for these. You can choose length and temperature. For this first beam, let's make it titanium. For the second beam, both the beams have the same width, so you don't need to define that again. For the second beam, the length, I'm going to pick a slightly smaller value. Initial temperature, slightly bigger. And let's do copper for this one. When you're defining mesh size, this is basically how small the grid sizes are that you're going to be simulating. So our simulation doesn't use a continuous heat flow equation. It creates a discretized grid of discrete cell widths. So this is basically defining how wide each cell is. If you have a higher number for this, your simulation will run faster, but it will be coarser. It will not be that fine. Versus if you choose a smaller number, it'll be more accurate, more realistic, but it'll also take longer. So once again, I'm going to pick a value that I know has worked before, but you can pick any value. And for our simulation time, we're going to run it for 1,000 seconds. Finally, you get to pick what kind of visualization you want, a 3D plot or a heat map. For this first one, let's just run a heat map. And then it'll immediately start running the simulation. You can see our beam 2, so the right side we defined as copper. And we can see that's heating up a lot faster than the left side, which is titanium. And this is analogous to what would happen in real life. Copper is a very good conductor of heat, so our results do make physical sense. So this will continue running for another a bit of time until it reaches basically 1,000 seconds. One cool backdoor that we've added is that if the difference between an old part of the time step and a new time step is so small, basically the changes are below 10 to the negative 3, the simulation will terminate. So you're not going to end up with a forever simulation if you just accidentally hit 10 million seconds instead of 1,000 seconds. It will terminate at some point when it just decides that the temperatures are not changing enough for it to care. I'm going to terminate this prematurely so we can look at the code.
So yeah, looking at the code, we can see this is where we measure user input. So like we saw previously, this is the code that you put in all the values. You put in the length, type of material, and it makes a struct of beam 1 and 2, which holds all those variables. Going down here we see the mesh size. So this again shows how fine the graph is going to be. And then this is where you choose the type of plot. You can choose a 3D plot, you can choose a heat map.
So over here, we're creating the actual representations of our grid. So for the purposes of the 3D plot, we create an x-axis and a y-axis. That's the length and the width of the beam. And based on that, we make a temperature array. This is a 2D array that stores initially basically what is our beam 1 temperature and our beam 2 temperature. So the left side of this array will be initialized to the beam 1 temperature, and the right side will be initialized to the beam 2 temperature. Furthermore, we calculate our time step. This might look like a really crazy, complicated, confusing formula to calculate the time step, but it's basically done to ensure that our stability condition is met, in that we are not choosing a time step that is too large that our results explode numerically, which is a risk if you don't have that stability condition. You can see over here we also do recheck for that stability condition and terminate the simulation if it will explode numerically. This is defining the Fourier number, which is what is actually used to calculate the change in temperature at every time step.
So here we can show you some of the code that's used to create the plots. So this right here is, you can see on the top, that's used to create the 3D plot that we didn't show. And then here, this is supposed to make a smooth color scale for the heat map. So we have the colder side's going to be blue, the hotter side's going to be red, and we have a smooth. It has 256 colors. That's supposed to make the color transition between the beams more smooth. And then we can show you down here. This is where we update the temp variable, which shows the temperature for the beam per time. So yeah, you can see here, it's a for loop essentially that runs until we reach a maximum time. That was again user input, right? And the draw now part here, we just keep updating it essentially. And yeah, here's some of our functions.
Yeah, so we have a couple of functions that we use in this script. This is the get material input and the get positive input. Just because we were getting so many user inputs, we found it helpful to have a function that gets that input, adds it to the struct, and validates that it's a correct input. In the future, we also have more functions that are coming in related to our material assignment. You might see over here, it's a very clunky way of assigning materials, where if you wanted to add a new material, let's say you wanted to add wood as one of the materials here for whatever reason, you would need to go and add in each of the values manually and repeat this sort of formula. So in a future version of this code, we are going to have a function that takes in an outside file that has all of this data and creates a material struct. Let's maybe end by showing the 3D plot.
Yeah.
So we can see once again the full script running in action.
You just use like.
Yeah, I'm just picking random numbers. Let's do steel. Mesh size, we'll pick a slightly coarser mesh, same 1000 seconds, 3D plot.
And yeah, here you can see the. You have the. Well, essentially, it would start at time equals 0 seconds, and you can see as the beam runs, the height basically, or the z-axis represents a temperature, and the grid represents the beam. So you can see how the height's changing depending on the temperature, and eventually, the colder side is going to increase in height, the hotter side is going to decrease in height, and it's very similar to the heat map.
Yeah.